Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to determine the concavity of the curves which are given with a parameter. So we're given parametric equations and we're trying to tackle with one of the classical problems of Calc 1, determining concavity, and that is somehow tied up to the second derivative of the function with respect to x. But since the curves are parametrized, so we're gonna sort of like rewrite what it means to be the second derivative written in terms of the parameter t in this case. Without giving you much heads up, I want to show you that the first graph looks like this. Okay, so it's almost like following the graph of natural log x. Okay, and the second part we're going to be given, we're given in fact an ellipse centered at the origin with the orientation counterclockwise. So we're going to determine the concavity in that regard. So this may be a long video, so I'm going to split that into two parts and let's start.
All right, let's start with part A. We have x equals t squared and y equals ln t. We're going to find the open t intervals on which the curve is concave up or down. But before we jump into that, just observe that ln function is not defined for negative values or 0. So I should put here a cap that, we should only consider the interval 0 and infinity for t to start with, okay? And for concavity, I need the second derivative of the function. So let's go ahead and find that. So we need first the first derivative, and we have the formula dy over dt, dx over dt, right? So dy over dt is 1 over t, and dx over dt is just 2t. And simplifying that takes you to 1 over 2t squared, okay? And I'm going to take the derivative of that again. So let me just write this in the power form so that that's going to be easier for me to take the derivative later on. Okay, so for d squared y over dx squared, we had another formula. So it's d dt of the first derivative coming out of the first step. And the bottom is dx over dt. Okay? So here we go. I'm going to take the derivative of this dy over dx. So it's negative t to the negative 3. And the bottom is still 2t. So that makes it negative 1/2 t to the 4th, because this term is equal to 1 over t cubed. Okay? So now I have the description of d squared y over dx squared. That's good. And I'm going to look at the sign of that for different t values. And t values are ranging in between 0 and infinity. Okay? And 0 is not included, so I'm safe because I'm not dividing by 0 here. One conclusion here is that d squared y over dx squared is less than 0 for any t. For any t coming from this interval 0 and infinity. All right? So what that means in the sense of calculus 1, that y is concave down all over. So here, the graph of this function is concave down on 0, t, and infinity. Okay? And I want to visually verify this. And please go ahead and use your TI-84 to graph x equals t squared and y equals ln t. And make sure that your t min is something close to 0, okay? Because for negative values, your calculator is not going to give you anything, okay? You can choose your t max to be as big as you can, just to see the full picture of the graph. But go ahead and see the graph similar to y equals ln x, okay? And as you see that the graph comes with this direction here, the orientation. Okay, and it's concave down everywhere. So if you just graph the function, so it's concave down. All right, so our analysis is correct, and we got that sorted out here correctly by looking at the sign of the second derivative of the function. All right. And I'm going to finish this video right now, and please move on to my next video to see what I'm going to do for part B. All right, bye.